Hello everyone, my name is Salomon Dominique Edimo Kingue. I am a master student at the Universidade Estadual de Campinas in Brazil, and it's a great honor for me to be part of this Energy Simulation Summit to present you our research in the form of this poster. Our research is entitled Feasibility Study of FAWAG, WAG and Water Injection Schemes for Brazilian Pre-salt Carbonate Reservoirs. We know that carbonate formations are among the most important hydrocarbon reserves in the world. One notable occurrence of this carbonate formation is the Brazilian pre-salt carbonate reservoir, characterized by oil-wet formation and high level of heterogeneity. This Brazilian pre-salt carbonate reservoir also contains light oil with high CO2 content and high solution gas. Traditional recovery methods can be employed to increase oil recovery. It is the case of water injection and more lately of water alternating gas, also called WAG. Another recovery method that can have our attention, it is foam floating implemented in form of FAWAG, which can be used to increase oil recovery. We have to know that foam is a gas dispersion within a liquid phase, which is usually stabilized by surfactant. There are some challenges associated in Brazilian pre-salt carbonate reservoir. It is the case of the poor reservoir performance observed using traditional recovery techniques. These traditional recovery techniques, which always usually go with fingering, channeling, and gravity segregation. But also, in the Brazilian pre-salt carbonate reservoir, it has been noticed high solution gas and therefore a potential for gas reinjection contributing to the net zero initiative. Therefore, the recovery methods that have gained attention for Brazilian pre-salt carbonate reservoir are not only to obtain a higher oil recovery, but also to manage the solution gas produced. FAWAG appears as an innovative recovery method. FAWAG is just the implementation of alternate injection of water, surfactant, and gas to generate foam. It has the potential to enhance the oil recovery and also control the gas mobility, therefore offering a potential for better CO2 management, reducing the environmental footprint of the project. However, FAWAG also goes with high operational costs, and usually foam stability is a challenge when we implement foam flooding. The objectives of this presentation of this research is just to assess the technical and economical applicability of FAWAG injection for Brazilian pre-salt carbonate reservoir, and this will be performed through a practical comparison of FAWAG with WAG and water injection in terms of economic return, oil recovery, and gas mobility control. To achieve these objectives, we employ the following methodology, which can be separated in four main stages. We have the first stage here in orange, which is about the initial case study. The case study simply refers here to the reservoir model and its injection scheme, which can be water injection, WAG, or FAWAG. The second stage here in light brown is about the optimization process, where several variables are modified in order to achieve the best objective function and perform a reliable comparison among the production strategies or the case studies we have. The third stage here in yellow is a stop criteria, where we check whether all the case studies have been performed or no. And finally, the fourth and last stage in green is about comparing and evaluating the result and eventually giving some recommendation. As part of the methodology, we use the full PT, we had the PT reservoir, which is a synthetic model, but with real characteristics from the Brazilian pre-salt. This reservoir has a dual media with porosity supported by the matrix, while the permeability supported by the fractures. In terms of wettability, the matrix is all wet, while the fractures are intermediate wet. Considering the complexity of the recovery methods involved in the simulator, which is foam flooding, and the high level of heterogeneity of this reservoir, we made the choice to focus on a specific reservoir region that we call the PT reservoir submodel 1. In terms of initial injection cycle implemented, for WAG, it starts with 3 moles of water followed by 3 moles of gas CO2, while for FAWAG, it starts with 1 mole of water, then 2 moles of surfactant at a concentration of 0.1 weight percentage, and it ends with 3 moles of gas CO2. We have to keep in mind that one of the reasons we implement foam flooding is to control or to reduce the gas mobility, and we are going to see how this gas mobility reduction can be assessed. It can be assessed using the FM factor, which is the correction factor for the gas phase mobility reduction. This FM factor can be obtained through this empirical foam model equation in thermal simulator. In this case, we use stars from CMG. We have to notice that there are various approaches to model foam, but here we did a choice to go for the empirical model instead of other models, because the empirical model already enables us to capture the effect of foam on gas mobility. We can see here that this FM factor is a function of several other parameters that are related to surfactant concentration, oil saturation, water saturation, and other parameters. Through this other equation, we can see how the gas relative permeability in absence of foam is multiplied by the FM factor, which will rescale the gas relative permeability to obtain a new gas relative permeability in presence of foam. This is how foam changes or reduces the gas relative permeability and therefore the gas mobility. You have also here the initial foam parameters. You have to mention here that these foam parameters are default data from the simulator. So we just use synthetic data, default data from the simulator, as we do not have, for the moment, not yet, real lab data. The optimization algorithm we use is for Mascio and Sciozza 2016, which is the iterative discrete lighting hypercube with NPV, net present value, as the objective function. The optimization parameters we used in this study are from 3 groups. The first group, the G1 variables, are related to the development phase. Among those G1 variables, we worked with the well placement. For the G2L variables, which are related to the management phase and the life cycle production optimization, we used the maximum injection and production rates and the injection cycle size specific to WAG and FAWAG. The third and last group we used is the modeling variables. This is about the foam specific parameters. Taking a look on the result after simulation, in terms of economic return, we can observe that in terms of this economic return, NPV, FAWAG appears as the best production strategy as it leads to the higher NPV. Similar observation in terms of oil recovery, where FAWAG has the highest oil recovery factor and cumulative oil production. While in terms of gas recovery factor, FAWAG after optimization has the lowest gas recovery factor compared to WAG or water flooding. This suggests that FAWAG has a better gas mobility reduction potential than WAG or water injection. We know that during the optimization process, variables are changed in order to achieve the best objective function, in this case, the best NPV. Now, the specific changes for foam parameters, we have the lamellar density that has decreased. This decrease suggests the development of a more mobile foam. While on the other side, we have an increase of surfactant molar density and surfactant concentration. This suggests of a development of a more stable foam. From this observation, this could suggest that there is a balance between foam stability and foam mobility when we implement foam flooding. This increase of surfactant concentration we notice here has an impact. For instance, foam apparent viscosity here, according to this graph, seems to mostly increase with surfactant concentration for a specific foam quality value. On the other side, we can see how the gas relative permeability curve has been rescaled, or should I say has been reduced in presence of foam. The initial curve here in blue of the gas relative permeability is here, and then when we implement foam flooding, this gas relative permeability curve has particularly been decreased, and this decrease has been more important in the optimized case where the surfactant concentration has increased. This would suggest that gas mobility reduction by foam seems to increase with surfactant concentration. The key outcomes of our work is that FAWAG outperforms WAG and water injection, as we have shown, in terms of economic return, in terms of oil recovery, and in terms of gas mobility reduction. FAWAG also involves high operational costs. This is due to the additional costs that go with the surfactant used in the injection cycle to generate foam. And finally, the balancing of foam mobility and foam stability is critical for the success of foam flooding. We would like to thank the different entities and the different bodies involved in supporting this work and this research in a broader view, and particularly Energy Simulation and Shell. So thank you for your attention. It has been a great pleasure. It was a great honor, and I will be happy to receive any of your comments and any of your questions. Thank you.